Okay, so in the previous class we were looking at this problem of pack learning. So we considered a simple problem of binary classification and binary or general emery classification over a finite hypothesis class. So a hypothesis class is the class of classifiers that we want to learn from. And effectively what we showed was that if the hypothesis class is finite, then it is pack learnable. So when I say pack learnable, I mean that it is possible to achieve a risk that is close to the best possible risk you can achieve from this hypothesis class to within an error of epsilon, and this happens with probability at least 1 minus delta. Right? So we can get epsilon close to the best possible classifier in the class with probability at least 1 minus delta using a finite number of samples. And we characterize the number of samples, the minimum number of samples that is required. Right? What we showed eventually was that the number of samples to get epsilon close to the best classifier with probability 1 minus delta grows as whatever, it's at least 3 by epsilon square r of g star times log 2 times the size of the hypothesis class by delta. As long as you have these many samples, you are guaranteed to achieve epsilon delta error. Do you need these many samples? Maybe, maybe not. Right? That's it.
Need these many samples, right?
Which?
Minimum these many samples.
Okay, so as long as you have these many samples, you can achieve epsilon delta error. But there may be a way of doing the same with fewer number of samples. Because ultimately what we derived was a bound. And it says that epsilon delta error can be achieved with these many samples using empirical risk minimization, which is one particular approach. Now, there could be another way of achieving epsilon delta error with fewer number of samples using a completely different approach. We don't know. Right? Maybe there's a better way, maybe not.
I mean, the measure itself is different, some other thing, instead of empirical risk minimization, because this is a lower bound, right?
Okay, so the way I've written it, if you recall correctly, what we showed that if the exact statement is the following. If the number of samples is at least this, then there exists an algorithm such that the probability that r of g hat is greater than or equal to r of g star plus epsilon is less than or equal to delta. Right? It doesn't mean that there is no algorithm that takes fewer number of samples and achieves the same. Right? But anything, as long as you have at least these many samples, you can achieve epsilon delta error. It doesn't mean that if you have fewer number of samples, you cannot achieve epsilon delta error. That would require a completely separate proof. All right. Any other questions? Okay. So this, and if you recall, in the proof, all we required was Chernoff bound, right? In particular for Bernoulli random variables. That was the main tool that we used to prove this particular result. All right. But this particular tool doesn't allow us to say anything else beyond finite hypothesis classes. All right. Again, it does not mean that infinite hypothesis classes are not pack learnable as of now. Right? All we've seen is that finite hypothesis classes are definitely pack learnable because there is one particular algorithm, empirical risk minimization, that achieves epsilon delta error using a finite number of samples. In fact, using these many samples. Okay. So before we proceed, some clarifications or some points to motivate why we are doing things the way we are doing in this particular course. So So in general, how do concentration inequalities help? Recall that the goal is to bound probabilities of this particular form. So probability that the sample average deviates from the mean by an amount epsilon. That's the main, at least much of this concentration inequalities part of the course will be to derive bounds on quantities of this form. So one sort of more natural approach is you find the distribution of this particular random variable, which is the sample average.
Does it have to be a sample average or any random?
It could be more general. So I'll talk about that in a minute. But let's say that currently the goal is to derive bounds on the deviation of the sample average from the mean by an amount epsilon. Right. So even for this particular problem, the one approach could be you try to find the distribution. For instance, if the xi's are Bernoulli random variables, then you know exactly it's relatively easy to find the distribution. Of course, even that distribution is not very easy to work with. It involves some sort of a summation of binomial coefficients and so on. But you could try to simplify this to get a more reasonable closed form expression, perhaps a simpler closed form expression. But that again, it works only for the Bernoulli distribution. For a more complicated distribution, for example, a chi-square distribution or something like a Poisson distribution and so on, it would get a lot more complicated. Right? You may not be able to derive a closed form expression for this sample average. And so the approach that we will use is we use a Chernoff type bound for the average of IID random variables, because now even if you know the distribution of x, deriving the distribution of the sum of IID xi's could be a lot more complicated, except for some specific cases. Right? But on the other hand, if you know what the moment generating function of x is, and you know how to derive a Chernoff bound for x, then deriving Chernoff bounds for quantities of this form is almost trivial. It's a very simple form. Alright, so that's one immediate advantage that we get of Chernoff bounds over, let's say, just trying to work with the actual distribution. Alright, and so that's one motivation for looking at Chernoff type bounds instead of looking at the actual distribution itself. But also in many cases, you don't know what the exact distribution of xi is. We'll see examples later on in the course where even knowing the exact distribution of xi is not particularly important. For example, maybe all I know is that xi is bounded between -1 and +1. That is the only information I have. It could be any distribution. It could be uniform, it could be a highly skewed distribution. But in all of these cases, I still want to derive bounds on this particular probability. It may not be the tightest possible bounds, but this is the only information I have, so I have to live with it. But we'll see that even in that case, even when the information that is supplied to me is limited, I can still derive bounds on this particular quantity. So that's the power of these concentration inequalities, as we'll see. And in many cases, this particular approach is good enough. Even in the case of Bernoulli random variables, for many problems of interest, the bounds that you derive using these Chernoff type inequalities could be off from trying to do it using the exact distribution, but it won't be too far away. Because in many problems in machine learning and computer science, ultimately we are interested in the dependence or knowing how this probability depends on certain parameters of the random variable and n. So typically the dependence on n is more important than anything else, and these Chernoff type bounds kind of give you the best dependence on n. Alright, and we are happy with that. Even if it is off by a universal constant, it's not particularly important. That won't be relevant to us. So these Chernoff type bounds they don't give you the tightest possible bounds compared to knowing the exact distribution, but still give you the tightest possible bounds given the limited information you have and given the ease of use. Alright. But more generally, as we progress through the course, we are interested in not just deriving bounds on the probability of the deviation of sample averages, but potentially more complicated functions. And these functions may not even have a simple closed form expression. So here is a sort of one example. So suppose I have n IID samples drawn according to some distribution, a discrete distribution, let us say, and I want to derive similar bounds on the number of distinct values that I see in this particular sample. Okay, so for example, if I'm just looking at coin tosses, the number of distinct values can either be 1 or it can be 2. Right? The number of distinct values is 1 if, let's say, I get a sequence of all heads or all tails, or it's equal to 2 if I see both at least one head and one tail. Alright. Now clearly I can't express this as a sum of IID random variables. Alright. But even then, this sort of approach that we will take will allow us to derive bounds on this particular quantity. Right. As we deal with such inequalities, we'll also see a number of more complicated looking examples. Alright. So that's some motivation for studying concentration inequalities and how they can be useful in algorithms, in analyzing randomized algorithms, in machine learning, and various other problems. Alright. Now this, after all, it's a short course, so we won't be able to see the full spectrum of all kinds of applications of this, but we'll try to see as many examples as possible. All right. The other perhaps motivation is why do we, what is the point of deriving bounds for pack learning, or the benefit of analyzing machine learning from a very theoretical and from a very theoretical perspective. Right? When you already have algorithms that do well, then what's the point of approaching it from this very statistical perspective? So again, we can think of different approaches for designing learning algorithms. One particular approach is, suppose you are given a particular machine learning problem, you can try different algorithms and keep trying to improve upon the algorithm to come up with something better and better and better. But then at what point do you stop? Is there a more systematic approach of designing a learning algorithm? And how do we even know whether you can do anything better than the best possible learning algorithm that we currently have? So is there a fundamental limitation? What are the fundamental limitations to the performance of any given learning algorithm? So that is going to be the main perspective that we will take in the statistical learning theory course. Given a problem, which is of course abstractly stated, what are the fundamental limits to the performance of any possible machine learning algorithm on this particular problem? It could be, we start with, of course, simple problems like classification and regression, mainly supervised learning problems. But even for this, how do we know what are the fundamental limits? And this will also allow us, so it's not to derive fundamental bounds. These bounds are important because they tell you what is the best possible that can be performed. So once you have a bound and you have an algorithm that gets close to this bound, then there's no point in looking much further, right? Because you know that you've already achieved something close to the best possible, right? Ultimately, if you're running a race and you don't know where the finish line is, then what do you do? So in a sense, learning theory tells you where the finish line is. All right. And while that is one advantage, the other point is that using this particular approach, we'll see certain fundamental principles that can be used to design learning algorithms. So one principle that we've already seen is empirical risk minimization. We've seen that empirical risk minimization can perform well. In fact, later on in the course, we'll see that for many supervised learning problems, the best learning algorithm can't do too much better than empirical risk minimization. at least for classification and regression problems. But of course, there are other issues of computational complexity and so on that we will not get into in this particular course. But of course, under those assumptions, empirical risk minimization is the best that you can do. And in fact, many of the modern learning algorithms still perform training using empirical risk minimization. Of course, they use some relaxation of empirical risk minimization in different ways to achieve a lower computational complexity, but at the heart of it, it is still empirical risk minimization. So, learning algorithms aside, you also want to know how do you choose your hypothesis classes. Right? We've seen that if you have a finite hypothesis class, it is pack learnable. Now suppose I give you a hypothesis class that is not pack learnable, then it means that there is no algorithm, irrespective of how you perform this training, it's not possible to do effective learning for your classification or regression task. Alright? Which means that that's a bad hypothesis class. So you should look for a hypothesis class that is better, that is pack learnable in some sense. We'll explore more of this as we go on, but this is just to give you a preview of what we want to do in this later on in this course. Alright. So how do you design these or how do you choose these hypothesis classes and will be determined by whether something is pack learnable and so on. And how do you do learning on these is what we will explore. Yes, there is a question.
Did you just mention between ERM is the best we can best?
In a sense, it is the best. Again, I was not precise in terms of what I mean by best. All right. So what we will show is that if you want to do pack learning, purely in terms of the minimum number of samples, right? What is the number of samples that is required to achieve epsilon delta error? All right. It turns out that you can derive a lower bound on how many samples are required to achieve epsilon delta error by any learning algorithm, and we'll see that ERM can get to this within, let's say, a multiplicative constant or so.
You also mentioned in the start that there can be other algorithms.
There could be. I mean, this statement does not say that there cannot be any other algorithm that does better.
Yes, there could be. So that approach will be better than ERM, right?
But what is that approach?
You only said that there could. Okay.
There could doesn't. I mean, it doesn't mean that there aren't. But can you find an approach? And is there a point in looking for a better algorithm? Right? What we'll see later that yes, there could be algorithms that do better, but any of those algorithms are not going to give you too much benefit. Right? The additional benefit that you would get would be very marginal. All right.
Sir, when you said finite hypothesis classes,
Yes.
can you elaborate what you meant by that?
So I mean that if you recall, when I set up the learning problem, the goal is to find, all right. So a hypothesis class is just a collection of functions, a collection of classifiers, right? So one example of a hypothesis class is the class of all, let's say, polynomial classifiers, which means G consists of all functions that can be written in terms of polynomial of finite degree. Or it could be the class of all linear classifiers, which is the class of all linear functions with whatever a certain thresholding and so on. All right. So this what we have shown so far is that if this class of functions is finite, there are only finitely many functions within this class, then it is pack learnable. Okay. It doesn't mean that infinite hypothesis classes are not pack learnable, but whatever finite hypothesis classes, if you think about it, it's not a very interesting class, because most natural hypothesis classes that you can think of, be it linear classifiers or polynomial classifiers or neural networks, they are all infinite hypothesis classes.
When you mean infinite, it is countably infinite or uncountable?
Doesn't matter. So far we've only shown that for finite classes. In general, it could be countable, it could be uncountable. In fact, if you think of linear classifiers and polynomial and neural networks and so on, they're all uncountable hypothesis classes.
I mean polynomial classifiers, if you're taking coefficients as only q, then it could be countable.
Fair enough, yeah, that's true.
So wouldn't the complexity be less if it is just countable?
We'll see that it doesn't make a difference.
Okay.
But in finite we can achieve like a faster convergence rate rather than searching in an infinite set of classes.
The trade-off between finite and infinite is not so clear. Okay, I don't want to get into it in too much detail, but but ultimately what you want to do is solve some kind of an optimization problem, right? Which is to find the minimum, this particular minimum of some function. Although if it is finite, the space of solutions is smaller. If the function is nice enough, then you can do much better if the space is infinite. Because you can use algorithms like gradient descent and so on, you can use more efficient search algorithms compared to what you can do if you have finite classes where the space is very large. It could be finite, but if it is very large, then it's much more difficult. Any other questions? Okay, so another point, just to sort of drive home the point that the point about concentration of the empirical risk. So what we showed was that if you pick any particular G, any fixed classifier G, then the empirical risk for this particular classifier converges or concentrates around the expected risk. That's what we showed. But then this does not hold true if I take G to be the empirical risk minimizer. Right? Because the empirical risk minimizer, or at least the empirical risk of the ERM solution, cannot be written as an average of IID Bernoulli random variables. So let's see a very specific example to see why this is not the case, just to get the concepts clear. Alright, so let's take a toy example where the feature space is the set of all real numbers. Okay, and I'm just looking at a binary classification problem. The hypothesis class is the class of all possible indicator functions on R. Okay, so you can parameterize it using the set A. So A is a subset of the real numbers, and it's simple. So g of x is equal to 1 if x belongs to this set A, and it's equal to 0 if x does not belong to the set A. Alright. Clearly, this hypothesis class is not finite. It's an uncountably large hypothesis class. Okay. Now, basically, if you take any fixed set A, right, you fix a particular A, which means that you're fixing the function g, then the average risk for this GA is just the probability that g of x is not equal to y. We're assuming that x comma y are drawn according to some distribution pxy. X comes from some continuous distribution. Okay, but I'm still using the notation pxy to interchangeably between discrete and continuous, just to avoid any, just to remain consistent. The empirical risk is, of course, again, it's a sum of IID Bernoulli random variables because I'm fixing a particular A. And so what is the expected value of the empirical risk?
R of G.
Yep, it's equal to R of G. Okay, nothing special going on here. It's again a sum of IID Bernoulli random variables, so I can just use the Chernoff bound and show that the probability that this deviates from the empirical risk deviates from the expected risk by an amount of epsilon is less than or equal to 2 to the minus some constant times n times epsilon square. Okay, just using Chernoff bounds. Alright, just that nothing new. This is exactly what we have seen in the previous class. Alright. Now, again, let's assume that I observe n IID samples. My data set consists of n IID samples, all drawn from this distribution Pxy. And I try to find the empirical risk minimizer for this particular data set. Take any arbitrary data set. Okay. And here is one. Now, in general, the empirical risk minimizer need not be unique. There could be multiple solutions G that achieves the same minimum empirical risk. That will happen in general. And if there are multiple, then typically we choose one of them. All right. So let's look at one little example where, say, I have 8 points, 8 samples, okay, which I've drawn over here. There are 8 points. The points labeled brown are the points corresponding to 0, y equal to 0, and the points in green are those which correspond to y equal to 1 in this particular data set. Okay, and let's suppose that this occurred at minus 0.5, 0.2 and 1.5. Just a talk example. Okay, so now let me take this particular set. Okay, minus 0.5, 0.2 and 1.5, and look at GA. So GA is a function that takes value 1 only if x is equal to minus 0.5 or 0.2 or 1.5 and is equal to 0 everywhere else. That is the function. What is the empirical risk that is achieved by this particular GA? It is 0, right? Because my data set consists of these points, it achieves 0 risk. It's correct for all of those points. Alright, do you all agree? So this particular classifier achieves 0 empirical risk on this particular data set because it is the empirical risk minimizer and there is one solution which achieves 0 empirical risk. But what is the average risk for this particular GA? Let us assume that Px is Gaussian, okay, some continuous distribution. What do you think the average risk would be? So remember, Rs, so GA is the function that is equal to 1 only if x is equal to minus 0.5 or 0.2 or 1.5. Okay? And it's equal to 0 everywhere else.
1 into 3 by total number of points plus then again.
What do you mean 1 into 3? So this is the average risk, right? So this is basically the probability. This probability is taken with respect to x and y that GA of x is not equal to y. As long as Pxy is non-trivial, that is, there is some, let's say, an interval along which xy is equal to 1. So y is equal to 1. what do you think this is going to be? Okay, but even if you don't know the exact distribution, you can still say something about this. So, so effectively, right, what GA of X is doing is it's outputting 0 effectively with probability 1, right? Because the output of GA is equal to 1 only on these 3 points, right? But what is the probability that X lies in A? 0. The probability that X lies in A is equal to 0. So with probability 1, this particular classifier is outputting 0. Correct? So what is the probability that this will make a mistake? So it's the probability that Y is equal to 1. Right? Which is something non-trivial, so perhaps significant, maybe half. Right? So no matter what you do, right? In fact, it didn't matter whether this was a particular example that we saw, but as long as this set A is finite, right? The same conclusion would hold. So as long as you have finitely many samples, in fact even countably many samples, this particular empirical risk minimizer can never achieve a vanishing probability of error. Right? The probability of error is always the probability that Y is equal to 1. Right? Which means that the empirical risk is nowhere close to the average risk, irrespective of what n is. Right? Is this okay? Any questions?
So whether GA of X is independent of Y?
I'm sorry? I didn't get.
GA of X is independent of Y?
G of X, if G of X is in this case, okay. So statistically, GA is going to be independent because it only depends on the data set. Alright? I didn't quite.
Actually, I wrote the expression by law of total probability. So I have probability of GA of X equal to 0 and Y joint probability of GA of X
Correct.
equal to 0 and Y equals to 1.
Correct.
Plus of G of X probability of joint probability of G of X equals to 1 and Y equals to 0.
Correct.
So that's I'm asking whether this GA of X and Y are independent.
In general, no, but here it's just because the probability that GA of X is equal to 1 is 0. Right.
Sir, what conclusion does this whole process draw?
This basically, okay, this is just to demonstrate that the empirical risk cannot be expressed as a sum of IID random variables, and therefore you can't directly use Chernoff bounds to bound the deviation of the empirical risk from the average risk. That's one point that can be drawn. The other point, subtle point that you can draw from this is that if your hypothesis class is in a sense too rich, in this case I'm allowing all possible classifiers. Right? This is indeed the set of all possible binary classifiers on R, if you think about it. And this says that if I take the set of all possible binary classifiers on R, then it's a hopeless situation, because even irrespective of how many samples I have, I can never achieve a small enough expected risk. Alright? And we'll see later that that's exactly why you have to restrict G in some sense. Unless you restrict, if you keep your G too rich, then you'll do extremely well on your training data set, but on a new sample, you don't generalize well enough. That is, the average risk on an independent sample can never be made arbitrarily small. So you can achieve good generalization error or average risk only if G is sufficiently restricted. And this phenomena that we've seen over here is what is called overfitting. You achieve zero empirical risk, but your average risk is very large. Okay. Any questions?
Does this also draw a point towards like a relationship or an inequality between the empirical risk and the average risk?
In what sense?
Like empirical risk may always be less than the other.
Not necessarily. It is not necessarily true. Right. So this basically says that the empirical risk could be very far from the average risk. It need not be close to the average risk. But in the case of finite hypothesis classes, because of concentration inequalities and the union bound, you could show that these two are close to each other. Okay. So basically the bottleneck here was that although for a fixed A, the empirical risk is close to the average risk, we don't have this property holding for all functions in the hypothesis class, because now I can't take a union bound because I have uncountably many functions. Right? And that's where the technique breaks down. Right? Okay. So here are a couple of exercises. Anyway, this will be in the notes which will be posted in the web page, so you can take a look at them more carefully. So a useful class of random variables that we will revisit later on when we explore learning theory in more detail, particularly binary classification, is these random variables called Rademacher random variables, which is, you can think of it as nothing but a shifted version of Bernoulli random variable. So Rademacher random variable is a random variable that takes +1 with probability half and -1 with probability half. Okay. What I want you to show is that the probability that if you take any vector A, any real valued vector A, then the probability that the inner product between A and X, or summation I equal to 1 to n ai xi, the probability that this deviates from 0 by an amount delta decays exponentially in delta square. I think there's an n here. Again, this is nothing but just an application of the Chernoff bound, but you will need to tweak the Chernoff bound in just a little bit, because if you think about it, the hint is to basically use, this is a sum of random variables, summation ai xi. They're all independent, but they're not identically distributed, right? Because ai xi takes the value ai with probability half and minus ai with probability half. Okay. What is the mean of this random variable? It's 0, right? Because xi has mean 0, ai xi also has mean 0, the sum of the ai xi is also is equal to 0. What is the variance of summation ai xi?
Summation
summation
A square.
ai square, right? So the variance of summation ai xi is summation ai square, or in other words, the 2 norm of a whole square. All right. So basically, this probability can be upper bounded by e raised to minus some delta square n divided by some constant times the variance square. Okay, I'm making this particular point because this will be kind of a recurring theme in the next couple of classes. This variance will occur very frequently. Okay, so the basic idea is just the same. You just apply Chernoff bound for sums of independent random variables, and then you'll need to simplify it a little bit so you can make use of the property that e to the power x plus e to the power minus x by 2 can be upper bounded by e to the x square by 2. Okay. All right. So now along the same lines, let's try to derive a Chernoff bound for Gaussian distributions. All right. So in your homework, you have to derive the moment generating function for the Gaussian with mean mu and variance sigma square. So hopefully you've done that. But anyway, I'll just use the fact that the moment generating function of a Gaussian x is e raised to mu times t plus sigma square t square by 2. Okay. Now, what does the Chernoff bound tell us? What is the probability that x minus mu is greater than or equal to some particular delta? Yep, so phi x of t divided by e raised to t times mu plus delta. Right, so in this particular case, this is just e raised to mu times t plus sigma square t square by 2 minus mu times t minus t times delta. So this mu t gets cancelled, so it is e raised to minus t times delta plus sigma square t square by 2. And this holds true for every t greater than 0. Right? Now this is not particularly useful because I have this hanging free parameter t. So let's try to derive the best possible Chernoff bound. Right? How do you do that? You can try to make sure that this is as small as possible. All right. So how would you minimize this particular function? Yeah. So one thing you have to be a little careful about is you have to make sure that the function, when you differentiate and set it equal to 0, you have to make sure that the function is actually convex. In this case, it is indeed convex. So what do you get if you set the derivative equal to 0? Okay, minus delta plus sigma square t to be equal to 0, or t equal to delta divided by sigma square. So the probability that x minus mu is greater than or equal to delta is less than or equal to e raised to minus t delta by delta square by sigma square plus sigma square by 2 times delta square divided by sigma power 4, which is e raised to minus delta square by 2 sigma square. Okay. So which means that the probability that x, you can again derive a similar bound on the, this is a the probability of deviation for the right tail. You can also derive a similar bound for the left tail, and it will be exactly the same. You can also show that the probability that x minus mu is less than or equal to minus delta is also less than or equal to e raised to minus delta square by 2 sigma square.
So in all examples, we are saying that for mostly all the random variables, the probability concentrates around the mean.
Okay.
So is it true for all? Or is there any other random variable that such that if you do summation, they don't concentrate about the mean? The distribution of mean does not concentrate about the actual mean.
So one thing is from the weak law of large numbers, right? We know that the average will always tend to the actual mean, right? The sample average will converge to the mean in probability. So the probability that the sample average deviates from the mean by an amount epsilon for any fixed epsilon greater than 0. So for any random variable x with expected value of x equal to mu, which is finite, this is always true, right? This is what we're guaranteed, no matter what happens. However, at what rate does it converge to 0? That can depend. Maybe it goes to 0 as 1 over log n, or 1 over log n, or 1 over square root of n, or 1 over n, or e to the minus n. That depends.
So I meant was like, so is there high dimension probability if you just transfer, like if you do a kernel transformation? So in high dimension space, they will always be empty. Most of the space will be empty. Probability in the probability space.
Sort of, yes.
Like this also, if we extend this.
Yep.
to high dimension.
Yes.
Does this hold every random variable, for any kind of?
It's a bit of a very generic statement. So again, for now we're only looking at sample averages, right? But this need not happen in general. So there's a separate theory of anti-concentration which tries to say that things do not concentrate about their mean in a certain sense. But again, what does it mean to occupy all of space? It depends. You can look at more complicated functions of n random variables such that they are as far apart as possible. But averages behave nicely because they always converge to the mean.
So for uniform distribution,
Yeah.
where even the space
That's for one uniform random variable. But let's say now I take an average of n I
That I
random
just
variables.
tend to
Yep.
concentrate because of
Correct.
CLP.
Correct. Yes.
But I think his question was for one particular random variable.
For one particular random variable? Okay.
Sum of random variables.
I'm myself confused.
Yeah, the kind of random variables and the kind of functions that we're looking at have a lot of structure to them. They're not arbitrary, right? For instance, we're looking at IID random variables, not highly dependent random variables, because their things could be very different. And we are also looking at reasonably good functions like averages, not something that is totally wild. Okay, so for the Gaussian random variable, we've derived a bound on the tail, and this happens to decay as e to the minus delta square by 2 sigma square, right? Which is essentially what I asked, or gave you as an exercise. If I have IID Rademacher random variables, then the probability that this deviates from its mean by an amount delta is also e to the minus delta square divided by 2 times the variance. Alright, so we've seen two different classes of random variables, the Gaussian and Rademacher random variables. In both cases, this tail probability happened to decay as e to the minus some constant times delta square divided by the variance. So does this happen for a more general class of random variables? Can we say that, or can we try to characterize all possible random variables for which this probability that this deviation happens at a rate e to the minus delta square? Okay, so that will be the goal for the next 1 or 2 classes. All right. So in fact, we'll show a very general theorem which tries to characterize all the random variables for which this tail probability decays as e to the minus delta square. And for such random variables, if you look at the average of n IID copies of this random variable, then it will decay as e to the minus n times delta square. Alright? So we start out with this particular theorem, which says that if I have a random variable x, then all of these statements that come below are all equivalent to each other. Now each statement involves a particular constant, k1, k2, k3. Each statement, the ith statement has some constant ki, and now this constant is not necessarily unique in this particular statement, but for example, if for a random variable x, if statement 1 holds with a particular k1, then it means that in statement 2 you can choose k2 to be some universal constant times k1, and in statement 3 you can choose k3 to be a universal constant times k1, and so on and so forth. Okay. So the first statement is, so let's say that I have a random variable for which need not have zero mean. Okay, the mean could be anything that is finite, but the probability that mod x is greater than or equal to delta decays as e to the minus delta square divided by some constant. This holds true for all delta greater than or equal to 0. So it has a tail that decays essentially at least as fast as a Gaussian, right? Because we've seen that for a Gaussian, the tail decays as e to the minus delta square by 2 sigma square. Alright, so these are all of those distributions for which the tail decays at least as fast as the Gaussian. Not all random variables satisfy this property. Alright. For these, you can show something. You can show that the moments, the pth moment of such a random variable can be at most as large as k2 times square root of p. Okay, so along those lines, here is also another exercise. So show that if x is a random variable, it's a Gaussian random variable, then you can derive an exact bound on the pth, or an exact expression for the pth moment of mod x. This is what it will turn out to be. But you again, using Stirling's approximation, you can show that this quantity grows as square root of p for large p. Okay, so Subgaussian, so at least this random variable which has a tail that decays at least as fast as a Gaussian, the pth moment is some k2 times square root of p for all p greater than or equal to 1. Okay.
So you said expectation need not be 0.
Which one? Expectation need not be 0.
But then you are saying the probability that the absolute value of x is greater than or
Correct.
equal to.
Yes.
So you are saying it need not be around mean.
It need not be around the mean. That's correct.
Okay. So what do you mean by tail in that situation? Just something which is
So then it makes sense perhaps for sufficiently large delta. It becomes useful only when delta is reasonably large, because that still corresponds to a tail.
okay. So large
Alright.
from
So
wherever
for
it is
example,
situated.
yeah. So for instance, so this could be 0, this could be the mean. Alright. When I say sufficiently large, it means that if this particular bound could potentially be useful now a priori. Right? I have no control over the value of k1. I don't know what k1 is. And in principle, the right hand side, what is the maximum value the right hand side can take? 2, right? So this bound is essentially useless if the right hand side, anywhere where the right hand side is greater than 1. Right? You agree with me? Because I know that this probability is less than or equal to 1. So this bound is essentially useless for those delta such that this quantity is greater than 1. Right? So what does it say? You take any particular delta. Now, for small delta, maybe this statement doesn't give me any useful information. If I choose a small delta, then I'm asking for the entire probability in this region plus the probability in this particular region. This probability has to be something. Now, for small delta, it doesn't matter what happens, but eventually as delta becomes large, it should be bounded by the tail of a Gaussian. Right? And in a sense, that is what you would expect, at least for a Gaussian. Even if you take a Gaussian random variable with mean not equal to 0, and you try to bound this particular quantity, then again you'll be able to show that the right hand side is less than or equal to 2 e raised to minus delta square by some constant. This constant may not be 2 sigma square when the mean is not equal to 0. This constant in particular could depend on the value of the mean. Alright, that's okay. But nevertheless, this bound holds. So this bound becomes useful only when delta is sufficiently large. if x is centered, then definitely this is what you would expect. But even if the random variable is not centered about 0, I still want this to happen. Okay? So similarly the moments of the random variable should be upper bounded by the corresponding moment of a Gaussian. And the moment generating function of x square, right? So e to the t square x square, it's not exactly the moment generating function, but the moment generating function evaluated at t square should be upper bounded by e to the some constant times t square. And this should hold for all t less than or equal to something, 1 over k3. Okay? And moreover, this expectation of e to the x square divided by some constant should be less than or equal to 2. That's another requirement. And if the mean is equal to 0, then I want the moment generating function to be upper bounded by some constant, e to the some constant times t square. So the moment generating function of the random variable should be upper bounded by the moment generating function of some Gaussian random variable. Okay. Now these statements may look very abstract and technical, but essentially the most intuitive ones are the first and the fifth. All right. Basically, the tail probability is upper bounded by the tail probability of a Gaussian of some variance, and the moment generating function is upper bounded by the moment generating function of a Gaussian of some variance. This is natural to expect. But we are listing out all of these properties, all of these equivalent properties, because for some random variables it may be more useful to use some of these properties over the others, because you may have a better handle on, let's say, the moment, or let's say this quantity, and so on. To prove different properties, we'll use each of these different ideas. Okay?
Will we be proving the equivalence of these statements?
I'll at least try to prove the equivalence between some of the statements, but the proof is also there in the textbook, high dimensional probability. But before we look at the actual proof, maybe we'll see some more properties. So even before that. So any random variable that satisfies these properties, or in other words, any random variable whose tail probability decays at least as fast as that of a Gaussian, is going to be called a sub-Gaussian random variable. Okay, it's a natural name. So tail decays at least as fast as a Gaussian, it's sub-Gaussian. But another point to note here, let's take property 1. Okay, suppose that property 1 holds for some value of k1. Okay, now if I replace k1 with a bigger number, what happens? Does the inequality still hold? Yes, right? So if I replace k1 with some k1 prime which is larger than k1, then the inequality still holds, because a larger value of k1 implies that this quantity is smaller, or this quantity is larger, or this whole thing is larger. Right? So definitely, if this holds for one value of k1, it holds for every value of k greater than k1. Correct? So it obviously makes sense to try to look for the smallest possible k1, and you can verify that this happens for every one of these properties. For example, if this holds for one value of k2, then it also holds for any k2 prime greater than k2. The same over here, here, and so on. Alright, so we want to find the smallest possible k for which this happens. And that smallest constant, which we will define using the fourth property over here, will be called the Subgaussian norm. For a given Subgaussian random variable, the Subgaussian norm is the smallest k such that expectation of e to the x square by k square is less than or equal to 2.
So we are defining it by this property, but it similarly it holds for other properties as well.
Now, I agree. I could try to define the Subgaussian norm using either property 1 or property 2 or property 5.
This is for particularly property 4.
For property 4, but whatever I would get using any of these other properties would be off by this by some universal constant. That's it. Alright. There are certain advantages of using this particular property. Some things become easier than others. Alright. But this also there's also another reason why we define the norm in this particular fashion, because it's connected to a more general class of norms over a general functional space. Okay, so this is a special case of a more general version of a norm on some restricted class of functions. Okay.
So what is that phi 2?
So this is just a notation to denote that this is a Subgaussian norm. Okay, because so norm subscript 2 will typically denote the L2 norm. Alright. Similarly, the Subgaussian norm will be denoted this norm notation with subscript psi 2.
And from the previous theorem, all random variables are Subgaussian.
So basically, if x satisfies one of these properties, then it satisfies all of the other properties, because all the properties are equivalent. Okay, so therefore, a random variable that satisfies all of these properties will be called a Subgaussian random variable. Okay. Here's an immediate example of a random variable that is not Subgaussian. Alright, you can take fx to be e to the minus beta x divided by beta for x greater than 0. So it's a non-negative random variable. So this will have a tail that decays as e to the minus delta and not as e to the minus delta square. Right? That's natural to see over here. E to the minus delta square for delta growing decays much faster than e to the minus delta. And this, you know exactly what the tail decay is, or the right tail decays. It is e to the minus some constant times delta. Alright. So this is something that is not Subgaussian. So it means that not all random variables are Subgaussian. So some basic properties of Subgaussian random variables. Let's see, observations. So let's say that I have a random variable x. So you can think of the space of all Subgaussian random variables. Effectively, what is a random variable? It is a function, remember. although we call it a variable, a random variable, it's actually a function from omega to r. Right? So the class of Subgaussian random variables is a class of functions. Alright? And so the first property is, let's say that I take a Subgaussian random variable x. X is Subgaussian. Then, and you look at alpha times x. I claim that alpha times x is also Subgaussian. And in fact, alpha times x is Subgaussian with norm. What do you think would be
Same.
the Subgaussian norm of
x1. Sorry,
I
x.
should say,
It should be scale.
yeah, scaled by mod alpha. Because alpha could potentially be negative. And how do you prove this?
First we need to show that it will still satisfy one of the equivalent conditions.
Correct. But more easily, I have it right here. So Subgaussian norm, the definition of the norm. Right? So let's suppose that since let's say that it has some Subgaussian norm. Let's say that this has Subgaussian norm equal to k. Then what is expectation of e to the alpha x square divided by alpha square k square? I know that x has Subgaussian norm k. What is this equal to? Or what is this less than or equal to?
Why in the denominator alpha?
I'm looking at this particular quantity. Okay. So let's call this random variable y. Okay. Y is equal to alpha times x. Then what is expected value of e to the y square divided by 2 k square? Sorry, alpha square k square. This is exactly equal to expectation e to the x square divided by k square. Right? Nothing fancy here. Which I know is less than or equal to 2 because k is the Subgaussian norm of x. Right? And this can't hold true for any smaller value of k, because then that would violate the Subgaussian norm property of x. Question?
Those properties which we define, are they necessary and sufficient condition for being a
Yes.
so means that
Yep.
for existence of Subgaussian norm is also a necessary and sufficient condition.
Yes. Finite Subgaussian norm.
So if it does not exist for a random variable, it means it's not a sub.
Yes. So for example, if expectation of e to the x square by k square can never be made less than or equal to 2 for any finite value of k, then it means that it is not Subgaussian. Alright? Any questions? Okay, let's try to evaluate the Subgaussian norm for a Gaussian random variable. Alright. Let's, just for convenience, let's assume that x is Gaussian with mean 0 and variance sigma square, general variance sigma square. Then what can you say about x square?
It belongs to chi-square.
It's a chi-square distribution, and you can show that the moment generating function of the chi-square distribution is equal to 1 divided by 1 minus the power half. This holds true less than 2 sigma square. Okay, so to find the Subgaussian norm, I have to find that value of k such that expectation of e to the power x square by k square is less than or equal to 2. Alright, which is nothing but the moment generating function of x square, which is evaluated at 1 by k square. Right? The smallest value of k for which this quantity is less than or equal to 2. Right? Or effectively, the largest, if I can find the largest t such that then I'm done. Right?
What are you trying to do?
I'm trying to find the Subgaussian norm for a Gaussian random variable with mean 0 and variance sigma square. Okay, so by definition, the Subgaussian norm is the smallest value of k greater than 0 such that this quantity is less than or equal to 2.
Sir, sorry for disturb, but how do you find norm of the random?
This is a definition, right? Okay. I still have not proved that this is a norm. I'm calling it a norm, but as of now, this quantity is just a definition. It's the smallest value of k greater than 0 such that this property holds. Okay? And since it's a sub-Gaussian random variable, I know that there exists at least one k, positive k such that this happens. Therefore, it makes sense to talk about the smallest k for which this happens. Right? If I want to prove that this quantity is actually a norm, then I need to show that it satisfies certain properties. One, that is, it's equal to 0 if the random variable is 0, or in other words, it's a constant. The second is something that I've already shown, that alpha times the norm of alpha times x should be equal to mod alpha times the norm of x. The third property I need to show is triangle inequality. For any two random variables, could be arbitrarily correlated with each other, as long as they are sub-Gaussian, then the norm of x plus y is less than or equal to the norm of x plus the norm of y. Okay, it's only then that I can conclude that this quantity is actually a norm.
So why can't we just
it's not enough, right? You can't conclude that it's a norm. Alright, because for it to be a norm, it has to satisfy certain properties. Now, again, I won't delve into the details of why it's a norm.
Sir, but the properties that you are saying are basically derived from the definition that you made.
Which one?
Sir, for Subgaussian norm.
Correct. You mean which properties are you talking about? The properties 1 through 5 or are these?
These properties.
Correct.
So these properties come from the definition of the Subgaussian norm that you
Correct.
told.
Yes.
And now you are telling that for a value to be norm, it needs to satisfy these properties.
So for something to be a norm, right? For something to be a norm, it has to satisfy. So f, so some function over a space, right? Let's call this space H to the set of all non-negative reals is a norm if it satisfies certain properties, that is f of x is greater than or equal to 0 for all x in H, and it's equal to 0 only if x is the 0 vector. So there has to be a notion of a 0 vector in this space. The second is f of alpha times x is equal to mod alpha times f of x for all real alpha. And the third is f of x plus y should be less than or equal to f of x plus f of y for all x, y, and h. I can call something a norm only if these happen. I have shown that at least that this happens for that particular thing. I called it a norm, but it satisfies at least one property of the norm. You can show that it satisfies all three properties of the norm. Okay, so basically I want to find what is the smallest k such that expectation of such that this quantity is less than or equal to 2. Right? Now I can all I have to do is just find that t such that this quantity is equal to 2. Right? This has to be equal to 2. That's all that I have to do. Is equal to 2 or 1 minus 2 sigma square t is 1 by 4. Sigma square t or t equal to 3 by 8 sigma square. Right? And therefore the smallest k such that this happens, or k square is 8 sigma square divided by 3. Right? So the Subgaussian norm squared of a Gaussian random variable is equal to 8 sigma square by 3. This is not terribly interesting at this point, but later on we'll see, at least try to use these ideas to derive bounds on, let's say, bounded random variables. Arbitrarily distributed but bounded random variables. Okay? So, question?
So while moving from smallest k to finding equivalence with finding largest t, we have assumed that t is greater than 0.
T is greater than 0,
And
yes.
also, since it was less than equals inequality, we have changed to inequality. It means that the moment related function is increasing.
Correct. What can you say about this particular function here as a function of t? Right? As t increases, this quantity increases, or this decreases, or this decreases, therefore this is an increasing function of t. Correct. Just that.
It was not taken that way.
Yeah.
So our constants are belonging to the domain of positive reals.
Yes. So k has to be a positive number.
Number in the sense like natural numbers or real numbers.
Real number. Yeah. Real. Any other questions?
I also have an intuition that any random variable with mean mu and median sigma square, it's Subgaussian. If it is Subgaussian,
Mhm.
its Subgaussian norm must be bounded by the Gaussian and Subgaussian norm of Gaussian random variable with same mean and same variance. Because
No, that is not true.
this intuitively feels right.
No, it is not true. You can have random variables which could have a different, which could be bounded. The Subgaussian norm of a random variable with mean mu and variance sigma square need not be upper bounded by the corresponding or random variable or the Subgaussian norm of the Gaussian random variable with the same mean and same variance.
So intuitively, what does Subgaussian norm represent? Intuitively.
It's
If it is higher for some random variable, what does it mean?
it means if the corresponding Subgaussian norm is higher, then it means that in some sense the tail decays a little more slowly, or in other words, the probability is more widely spaced apart. If the Subgaussian norm is really small, then it means that most of the probability is concentrated around 0 or around the mean in general. Whereas if the Subgaussian norm is large, then it means that the probability is maybe slightly more widely spaced apart.
So was the thing that he said the opposite true? Like, is the Gaussian with same mean and variance upper bounded by Subgaussian with same?
Not necessarily. So you can't directly conclude. So all you can say is that if a random variable is Subgaussian with mean mu and variance sigma square, it can be the Subgaussian norm of this random variable can be upper bounded by the Subgaussian norm of some Gaussian random variable. Could be a different mean and variance, but some Gaussian random variable. I mean the Subgaussian norm itself is basically defined only for Subgaussian random variables. If a random variable is not Subgaussian, then this doesn't make sense. Right? Because if there's a finite k for which this happens, then it is automatically Subgaussian. For the exponential distribution that we had over here, you cannot find a finite k such that this quantity is less than or equal to 2.
So you said right, Subgaussian means the tails decay as
Correct.
fast as
Gaussian,
at
yeah,
least.
yeah.
So all Gaussians are Subgaussian.
Yes.
And at least as fast as Gaussian you said. So with the same mean and variance, they don't have any. As fast as Gaussian in the sense.
I mean, as I said, when I say as fast as some Gaussian
Some Gaussian.
with some mean and some variance. Any other questions? Okay, so let's stop here.
So instead of going through calculating moment generating function of x square, could we have just done it directly using e of x square by k square, then we would have taken that as a
Correct. Exactly. So depending on what random variable you take, for some random variables, bounding using, let's say, the moments could be more easy. For some random variables, maybe bounding the tail is more natural. For some, this could be more natural. For some, the MGF could be more natural. That's exactly why we have listed these different properties. Okay. Okay, so let's stop here.